All right, let's get right into it. Today, we're going to talk about one of the most powerful tools in any modern lab, high-performance liquid chromatography. You'll usually just hear it called HPLC, and honestly, it's a machine that lets us see the invisible world around us, and we're about to find out exactly how it pulls that off. So imagine you've got this chemical haystack, right? A super complex mix of stuff. It could be anything, a drop of blood, the wine you're drinking, maybe a sample of water from a nearby river. How on earth do you find and measure just one specific molecule in a sea of thousands, maybe even millions of others? That's the challenge. And the answer, you guessed it, is HPLC. It's pretty much the gold standard for this kind of work. Think of it as the ultimate sorting machine for molecules. It takes that messy liquid mixture, shoves it through a very special tube, and manages to separate out every single component with just incredible precision. So to really get how it works, we're going to follow a sample on its journey through the whole system. We'll start with the liquid that carries it, see how it gets injected under crazy high pressure, then watch the real magic happen inside the column. After that, we'll figure out how we read the results, and finally, we'll see why this amazing technology matters so much in our everyday world. Okay, our tour starts here in what I like to call the engine room of the HPLC. You see, before our sample can get sorted, it needs a ride. And that ride is called the mobile phase, which is pushed along by a seriously powerful pump. So the mobile phase is basically just a river of solvent that's always flowing through the machine. It's what picks up our sample and carries it along for the ride. Now, the exact makeup of this river is absolutely critical. Are you using something polar, like water, or something non-polar, kind of like an oil? That one choice completely changes how well the molecules get separated later on. And let me tell you, this river doesn't just trickle. To get through the next part of the system, a tube packed super tightly with tiny particles, this liquid has to be forced through under enormous pressure. We're talking up to 6,000 pounds per square inch. Some of the newer systems go even higher. That's the kind of pressure you'd feel miles deep in the ocean. It's just immense. Now, you've got two main ways to run this high-pressure river. The first is called isocratic. Think of it like putting your car on cruise control. The solvent mix stays exactly the same for the whole run. It's simple, but it's not always great for sorting out a complex traffic jam of molecules. The other way, the more powerful way, is gradient elution. Here, you actually change the solvent mixture as you go. It's like you're adjusting the flow of the river to help the slower-moving molecules separate out properly. It just gives you way more control. And look at this. It shows you the difference perfectly. Using that constant cruise control method, isocratic, it takes about 30 minutes to separate this mixture. But by using a gradient and changing the solvent as you go, you can do the same job in just 5 minutes. And look how clean and sharp those results are. It's not just faster, it's a whole lot better. For complex samples, gradient is a total game changer. Okay, so we've got our high-pressure river flowing. Now, here's the million-dollar question. How in the world do you get your sample into that system without, having it all explode from the pressure? It's a huge engineering problem, and the solution is just brilliant. It all comes down to a clever little thing called a sampling loop. Here's how it works. First, in the load position, the high-pressure river just flows right past the loop. Meanwhile, you use a normal syringe to fill that loop with a very precise amount of your sample. No pressure, totally safe. Then you flip the switch to inject. With a quick turn, that loop you just filled is suddenly sitting right in the middle of the high-pressure path. The mobile phase instantly rushes through, grabs your entire sample, and carries it off as a perfect, tight little band towards the column. It's elegant, and it works perfectly every time. And that brings us to the main event, the absolute heart of the HPLC. We're talking about the column. Everything we've done up to this point, the powerful pump, the perfect solvent, the clever injection, it was all just to get the sample right here. This is where the sorting actually happens. So what's inside the stainless steel tube? It is packed, and I mean packed, with what's called a stationary phase. Most of the time, it's just unbelievably tiny particles of silica, each one just a few micrometers wide. The best way to think about it is as a massive, microscopic obstacle course, and every single molecule from our sample has to navigate its way through it. And here's the secret sauce. The core principle is this. The smaller the particles you pack in that column, the better the separation you're going to get. It's that simple. Why? Well, smaller particles create a much more complex and challenging obstacle course, which gives all the different molecules more chances to separate from each other. In fact, this right here is exactly why we call it high-performance liquid chromatography. It's all about those tiny particles. Look at the chart. Older methods used larger particles, and the result was pretty low efficiency. The results were messy and blurred together, but when they figured out how to use these incredibly small particles, boom, the efficiency just skyrocketed. You get these beautiful, sharp, well-defined results. That leap in performance is the whole secret. So, our molecules have just finished a grueling race through that obstacle course. And because they all have slightly different chemistries, they don't all finish at the same time. Some zip right through, others take their time. They come streaming out of the column one by one. All we need now is a way to see them cross the finish line. And that's exactly what the detector does. It's our finish line camera. As each little group of identical molecules exits the column, it flows through the detector. The detector then sees them, often by shining a beam of UV light through them, and turns that sighting into a little electrical signal that a computer can read. And this is what the computer gives us, a chromatogram. It looks like just a graph with peaks, but it tells us two absolutely vital things. First, when a peak appears tells you what the molecule is. That's its chemical fingerprint, or retention time. Second, how big that peak is tells you how much of it there is. So with one simple graph, you get both the identity and the amount. It's incredibly powerful. Okay, the tech is really cool, I get it, but so what? Why is this technique so important? Well, let's take a quick look at where HPLC shows up in our world, because I promise you, it's pretty much everywhere. Seriously, think about it. In pharmaceuticals, it's used to make sure the medicine you take is pure and effective. In the food industry, it's analyzing the vitamin C in your orange juice or the caffeine in your coffee. Environmental scientists use it to hunt for tiny traces of pollutants in our water. Forensic labs use it to identify drugs. Doctors use it to help diagnose diseases. It is the hidden technology that underpins the safety and quality of so many things we rely on. So when you boil it all down, HPLC gives us the power to see the invisible chemical fingerprint of almost anything around us. It's the technology that's quietly working behind the scenes, making sure our food is safe and our medicine is pure. It's the ultimate sorting machine. And it really makes you wonder, now that we have this power to see the chemical makeup of everything, what other secrets is the world waiting to show us?